Okay, it's time to start. So let's start Wednesday's session. Today's first speaker is Professor Zhijun Qiao. His talk is on R matrix and n-dimensional integral systems associated with the Camassa-Holm hierarchy.
Hello, good morning, everyone. Thank you. It's my pleasure to be here, give a talk regarding integrable system associated with Camassa-Holm hierarchy. First of all, I thank my friend Het and Dr. Barter. What is his last name? I forgot. I think this is a great opportunity to do collaboration with people working on representation theory. So my title is R matrix related to Camassa-Holm hierarchy, but it's finite integrable systems. And this is of course in the area of integrable system. Here's my outline. I'm going to talk about a little bit background of the integrable systems on the symplectic manifold. The completely integrable system in the sense of a Liouville. After that, give some examples from integrable, finite-dimensional integrable systems. Then related to Camassa-Holm spectral problem, but use the constraint method. Basically, the method we call the nonlinearization method. That's a longer time developed by Professor Zhijun Qiao, China, Zhijun University. Let's start from very basic stuff. It's the symplectic manifold and Hamiltonian system. So the M2N is called the symplectic manifold. Suppose that manifold is equipped with differential two form. Of course, that condition stands for the non-degenerate. So so M at Tmx stands for the tangent space at the point x, because A and eta are the two tangent vectors. So that is non-degenerate condition. So that manifold is called symplectic manifold. Then we can do the local representation. So the local coordinates dxi and xi and xj. Take the wedge, and then w omega ij, stands for the coefficient. So it's basically satisfying the antisymmetric property. So if you do the computation on it looks like move very slow. Because eta are two tangent vectors, you can do the value at both vectors. So you have this value. The standard symplectic structure, so in this way, so suppose that R2N is dp by dq. This is a standard symplectic structure. So in this case, you can write it in the differential two form. There's the closed two form in the inner product way. The J is antisymmetric matrix. So capital E stands for unit matrix. So this is a little bit recall regarding symplectic manifold. And also in the symplectic manifold theory, there's a well-known double theory. So basically, a double theorem tells us locally all the symplectic manifold structure is a differential homomorphic to this standard simplex structure. Okay, under the standard simplex structure, of course, you can do Hamiltonian vector fields. So you can define vector fields as something like this. So suppose there's so M2N is a symplectic manifold. Then, as per the differential two form, you select arbitrary tangent vector on the tangent space. Now, of course, as per this formula, you can define one form omega 1. Okay, so basically you have this map So give Xe here, you define omega 1, so this way. So what is the property of this map between Xe and omega 1? It's here. So actually, this is the, it gives a unique linear isomorphism between is actually a cotangent bundle and a tangent bundle. Okay. So of course the condition omega 2 has to be non-degenerate. Okay. As per that definition, so suppose H is any function from this symplectic manifold to R. So this is called a Hamiltonian function. So then DH is called Hamiltonian vector fields. Okay. So canonical Hamiltonian system on this symplectic manifold, you can write it in this way. So if you put a standard symplectic manifold, now you have this canonical, the Hamiltonian equation. Okay. Now let's go to the Poisson bracket. Okay. Now suppose you have two functions, f and h. So the third function could constructed through a bracket defined the derivative of f flow along the Hamiltonian flow gh. Okay. Of course, this bracket sentence of a Jacobi identity. So basically, this bracket is linear algebra. Okay, the formulation, how do you compute or how do you calculate the Poisson bracket? Suppose you are given two Hamiltonian functions, f and h. So the relationship is this. So left-hand side is two functions make the Poisson bracket. Now you can do the two differential one form, but this is the IDH stands for, remember, that's the tangent vector, now you evaluate at point X. So this exactly, you use above the theory, you can compute it through the omega 2 form, the differential 2 form, evaluate those two tangent vector fields. Okay. So basically, Poisson bracket can be computed through the omega 2 form, evaluated at those two tangent vectors. In standard way, excuse me, if the simplex structure is a standard, now you can compute the Poisson bracket in a very good format. That's usually we use that to verify the finite system is integrable or not. Okay. So use a Poisson bracket, of course, the standard canonical Hamiltonian system can be written as the Poisson bracket of the coordinates qi with h, pi with h as well. So this is stands for the Hamiltonian is conserved. Okay. This is the literature regarding the symplectic manifold and integrable systems needed that part. So what does that mean? What does that mean the complete integrability in the Liouville sense? So first of all, let me give you the condition. There's two conditions called the Liouville condition. So first one, if you have a system mutually involutive functions, what that means involutive, which means those functions are in involution in Poisson bracket. In other words, all the Poisson bracket, is 0. Second condition is suppose you have this n functions, but give the level sets if and only if those functions are linearly independent on this level set. So basically, this level set will form as a manifold. So here's the Liouville theorem. So Liouville theorem is this is called the Liouville. Suppose this satisfies Liouville condition. Okay, this is a Hamiltonian system on the symplectic manifold. Then satisfy Liouville condition. Now we have following 4 results. First of all, that's level set invariant under that Hamiltonian flow. Second, this is an important part of or key part of Liouville theorem is a proof very law. So basically, that's level set is compacted and connected. Now, most of the cases in finite integrable system, we use that verify the condition, just to verify Liouville condition. We claim that this system is integrable in a Liouville sense. Okay. The third part is just, suppose you already have those, results, number 1 and 2. Then the third part is just on the angular coordinates, as a new coordinates on phi 1, phi 2. Then the system completely integrable. So because this is already a linear system. Okay. So number 4 is just automatically results from number 3. Okay. So this is a Liouville system. So what are the examples? Suppose you have system satisfy Liouville condition. So we just give you some typical finite, finite systems, how to verify the Liouville condition. Then we claim the finite system is integrable. So that's our idea. Now, starting very beginning, so there's an angular momentum. Okay, this is Poisson bracket is in standard way. This is canonical coordinates for the pi and qi. So based on pi and qi, we form the angular momentum b sub ij. Okay, most of the cases in finite integrable system, we use confocal systems. So this is alpha I, alpha j is parameters but not equal. So bij squared, just the angular momentum takes square. Now, what is typical for the integrable system in the finite system? So first of all, it's the Delaunay-Moser system. That's a longer time ago. Okay. The application system in the mechanical engineering is n-dimensional Kepler system. So actually, it's a theoretical physics or astrophysics used a lot. So this system, the H defined by the P norm square and the Q norm, but is reciprocal. So this is a Hamiltonian system. So it is integrable. So we can verify what? Just verify the Liouville condition, which is you need to figure out a system of independent functions which are in evolution. So here is our Poisson bracket. So this is a H Hamiltonian function. What is the system of independent? Such a Poisson bracket is just BK. Use those functions defined by Delaunay-Moser. Okay. So this is the first finite integrable system in Liouville sense. And we have more. Also based on that, Moser in 1975, you have this condition. So this is called confocal system. You can verify those functions formed by E sub ij, E sub k defined xk, yk plus gamma k is defined as this function. This is not a gamma function, I'm sorry. This is just notation for confocal system. Okay. So what is the relation to the Lux pair? Lux pair is, of course, by Peter Lux. So this is a Lux pair. Okay. So here A is matrix, L also matrix. So how do we find the system of functions which are in evolution? You just use, if you find the Lux pair, you just use L, take the power, now you take the trace. So this is typical the functions which are in evolution, which means a Poisson bracket equals 0. Okay. Based on that, the typical examples of total lattice, periodic total lattice by Fletcher is using this Hamiltonian. Okay. So now come to something related to our matrix to the finite integrable system use a constraint method. So let me go to just a quick review for the R matrix. Okay. So Smirnov-Tieshatsky, so the 1983. So suppose you have Lie algebra G. Okay, the G is given. Now you define a new bracket sub A B bracket sub R. R means the map between it's from the Lie algebra G to itself. Based on this bracket, define a new bracket. The new bracket left hand side. So right hand side is RA is its map is still in G, but here is plus not minus. So this is a new bracket called So our matrix satisfy this permutation, something like a Jacobi identity. This is our original definition by Smirnov-Tiensky. Okay. Now it's here. This is, for finite dimensional case, I put a G is decomposed to G plus and G minus. So basically, it's the projection for the positive part and projects to negative part. So our matrix is defined by 1/2 P plus minus P minus. Now later on, Fadjeev and Taklejai, so I applied the matrix, the algebra to this case. This is a tensor product. Suppose you have E sub I and E sub k. That's the basis. Now suppose this defined definition R is called our matrix. R must satisfy this Yang-Box equation. Yang-Box equation. Classical Yang-Box equation is sufficient condition to guarantee R is our matrix. Okay. So this is here R1 to R there's a permutation. Those bracket must be 0. This is a classical Yang-Box equation. Okay. Now the Weiss introduced our matrix. The basic idea is what? From left hand side is two matrices make the commutators, but here minus R1 to R2. If R1, 2 is our matrix, the left-hand side use the tensor product, but the bracket part in the matrix is doing the Poisson bracket. Of course, this is a matrix. So use the left-hand side to give a new Poisson bracket. This is called fundamental of Poisson bracket by Fadjeev and Taklejai. Okay. The idea is to construct a new Poisson bracket. The example I give here, excuse me. So this P is a 4x4 matrix. So you can rewrite that in this format. There's a Pauli matrices. Okay. There's an original thought by Fadjeev and Taklejai is like this. If you have L, a matrix, and R is our matrix, then has this two as above this fundamental Poisson bracket, you can rebuild another one. You can construct a new Poisson bracket. I'm sorry. Now, question is, suppose we have Poisson bracket. We have the matrix L, Lux matrix L. How do we compute or how do we construct our matrix? This is a major part of my talk. Okay, one of our ideas using Professor Qiao created the method called the nonlinearization method. Okay, let me give you the procedure or idea how to use or how to establish a finite integrable system using nonlinearization method. The starting point is from eigenvalue problem. It's an ODE, of course. So M is somehow matrix related to your potential function, or sometimes called the potential vector. Lambda is eigenvalue. Y is eigenfunction, or sometimes eigenvector. It really depends on M. Now the idea is finding the constraint relation, which means between your potential vector U and eigenvector Y. Okay, so F is the relationship between the eigenfunctions and potential functions. But how to find F, I will show you later on. Okay, after that, there's a key step, then plugging back U bar into a regional eigenvalue problem. Now a regional eigenvalue problem will lead to next equation, which is only Y involved, no U bar anymore. So this system usually is a nonlinear ODE system. So I mark here capital lambda stands for diagonal matrix of lambda, Y, lambda. Usually those are distinct the eigenvalues. So Y is the eigenvectors corresponding Y, 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 N. Each, the eigenfunctions Y, 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 N corresponding to each the eigenvalue lambda. Okay, After you have this system, you have this nonlinearization system. Of course, this ODE. So first step, you need to figure out that is Hamiltonian or not. You need to find H stands to satisfy this standard canonical Hamiltonian system. Now next, is this integral in the Liouville sense? You need to look for a system of functions fg such that the Poisson bracket equals 0. Okay. Now I give you the example. I'm going to use the problem from Camassa-Holm equation. So here's the PDE. Okay. So most of the work is selected so longer time from my paper. Okay. So this is a Camassa-Holm equation. This I put negative 2 because Camassa-Holm equation in the negative flow of a integrable system. Okay. So what is the eigenvalue problem corresponding to this equation, this one? Okay, so this is a second order differential equation. Now let me clarify. M is a potential function. M equals u minus u sub double x. So u psi is eigenfunction. Okay, this is called eigenvalue problem of the Camassa-Holm equation. This is found by Camassa-Holm 1993. So what I do here is figure out remember the constraint between the eigenfunction and the potential function, which is this key relationship. Left-hand side is a potential function, right-hand side the eigenfunction. But remember, capital lambda is diagonal matrix. U Q is the eigenfunction corresponding each eigenvalue. Okay, but the denominator is this inner product. Yeah, because the lambda Q and Q is a vector. So inner product makes a square. So this is a relationship we call constraint between the eigenvector, between potential function and eigenfunctions. Now plugging M back to the spectral problem of the Lux pair for the Camassa-Holm equation. Now you have this equation. Okay. So what is this? So this is I put, so this Qx equals P, Px equals minus this part. This put dot this part exactly corresponding to M. Okay, because you plug M into the original. Oh, I should stand here probably. Now it's plugging back to the spectral problem. Okay. Now question is that Hamiltonian? So we give the H plus. This Hamiltonian function is like this. Okay. I especially put this Hamiltonian is typically is different from peakon dynamical system. There's a peakon dynamical system. H function is created by Camassa-Holm 1993. So our Hamiltonian is different from theirs. Okay. Now we're gonna what? Next step, we're gonna remember as per the Liouville theorem, we need to verify this integrability using what? Using the system of independent function. We need to find a system of independent functions such that those functions make the Poisson bracket with H plus must be 0. So what I did is, so here create those functions. So still based on what? Those corresponding eigenfunctions, but it's lambda k plus 1. So as those cases for positive integers. So this is a determinant of those two matrices. Okay. Okay. So this one is there's a relation to the R matrix structure. I'm gonna show you in a moment. Okay. Just to tell you, so this constraint we defined earlier actually satisfies the Hardim equation, Hardim type equation. So since this conference is not special for solitary solution, I don't want to waste your time to show you how do we verify MS solution or verify the Hardim type equation. I didn't write the Hardim type equation here. So basically, the constraint is related to Hardim type equation. Okay, if you're interested, you can take a look at our paper. This is, of course, corresponding positive. So in integrable flow, there's a positive flow and negative flow. So this, I put plus, remember here, I put plus, which is corresponding positive flow of the integrable hierarchy, okay? So this is the first part for the positive. What about the negative flow? So let's do another constraint. So this is another constraint between the potential function and the eigenfunction, but this is a little bit complicated, but it's still, of course, a fractional form, okay? So I put it, Qj is corresponding. Oh, I should delete something. This is something wrong here on the bottom. Okay, you just understand that this equation is the relationship between potential function and eigenvectors. Okay. Now, remember, still the X form, but with a different constraint. You have this different system. So this is not, I put, which cannot have canonical form in R21. This is something related algebraic structure. You have to figure out new manifold because, so in whole space not, but if you put constraint, so this will put two constraints, then this system could be constructed as the canonical form on the submanifold. So that's why we introduce F and G. Okay, so on the submanifold, no longer whole space of Poisson bracket. So we need to redefine the Poisson bracket as a Dirac Poisson bracket. Okay, this right hand side, no D part is a standard Poisson bracket. So the Dirac Poisson bracket is on the submanifold. You have X term. Extra term depends on your constraint capital F and capital G. Under that, then this system can be rewritten as a standard Poisson bracket, which is here. So what is H minus? So under our new structure, H minus would be very, very simple. Let me show you. So you see here, very simple form. Okay, because you use the Dirac Poisson bracket. Now, we need to verify that system is integrable in the Liouville sense under Dirac Poisson bracket. So we need to figure out, you see here, this is the H. Now you need to figure out H, a system of functions such that the Poisson bracket with H minus is 0. I said it again, H minus stands for the integrable flow in the negative direction. So what is Fk? Fk is like this. You may wonder, how do I find Fk minus? So this part is a key part of in the time part. Remember, Lux pair, you have spatial part and time part. This is most of from an integrable system, so Lux pair, okay? So I tell you that this is produced from nonlinearization procedure of the time part, okay? Again, so this actually is the proven to the solution of the well-known equation, Camassa-Holm equation solution. So I gave the proof in that paper, but I show you later on. So just to give you a rough idea. Okay, now it's the integrability for the Newman-like Camassa-Holm system, which is on the submanifold, not the whole space. So now I'm going to show you the three things: constraint, our matrix structure, and how do we construct, how do we relate our matrix to integrability. Okay, now left-hand side is the constant, actually. I put the G minus 1. This is directly from the integrable system. It's a negative flow. So negative flow, first component, I selected constant. So right-hand side stands for what? This lambda G is lambda G Qj squared. Okay, so eigen function takes a square for each lambda sub J. Okay, this is the build-up of the relationship between the eigenfunctions and that number. So actually, this is what give you the constraint for the manifold. Okay, so you plug in everything there because we already computed. So that the equation number 1 is changed to this. use the simple form. So inner product form equals 1. You take derivative, you lead another one. It's exactly like a twisted the super surface. Now it's build up the your symplectic submanifold. Okay, so this here, you take another derivative based on second equation, you get this constraint. So this is the constraint, the procedure. How do we find the constraint? Now plugging back the Camassa-Holm spectral problem, you have this system and with two constraints. This is different from the positive direction. Now I'm going to see here Dirac-Poisson bracket. I showed you earlier. Is already covered. Let me jump to the next page. So what is our matrix? Remember, I didn't give you the integrability. So although I show you the FK, I'm going to show you right now. Use our matrix and figure out the system of function which are independent. Also, Poisson bracket have to be 0. So let's construct the matrix. So this is the matrix. I call the negative Lux matrix because of the integrable flow is negative flow. So this Lux matrix. Well, you use Lie algebra, it's very simple. Actually, it's in SL2, very simple structure. But in integrable system, you need to figure out, remember, the functions must be in involution. In other words, Poisson bracket must be 0. Otherwise, you cannot claim the integrability. So the idea is here, A minus, B minus, and C minus defined through the following 3 equations. You see, last part exactly is the confocal system. Remember in the very beginning of my talk, I talked about Claudius' work. But the first part different. You see here, those part, you see here, so from the reciprocal of the eigenvalue, the parameter lambda, here's -2, here -1. But the coefficient here is 1, 4. Here's the inner product. Okay, so this is our major matrix number 10. Now, what is the purpose of number 10? You do remember use created our matrix. Okay, remember. So we have Lux matrix. We have Poisson bracket. This standard form. Now we're going to do tensor product based on our L minus. This is tensor with the 2 by 2 identity matrix. You have L1. This is L2, but different parameter lambda and mu. So left-hand side is built up perfectly as per the fundamental Poisson bracket. Now right-hand side, you need to figure out what is it, R12 and R21. This is our matrix. Now you plug in all the computation, use a Poisson bracket on your left-hand side. So this is our computation for each entry on the left-hand side. So actually it's a Poisson bracket. Okay. Now R1, 2, and 2 are this relationship with P. P is a standard form, the 4 by 4 matrix. So actually it's written by standard form of the R matrix. Okay. So in our case, remember, in our case, what is the R12 and R21? Suppose L is already defined by the above that matrix A minus 1, B minus, and C minus. So here's our major results for our matrix. So R12 equals this, parameter lambda and mu, P. This is standard part, but with the tail part, S minus. So tail part a little bit different. So this is basically we call dynamic R matrix. It's not a constant R matrix. I'm sorry. Okay. So this is we also compare with the earlier results by those two experts in solitary theory, Ragnisko and Brodsky, the physical AE 1996. Our results are also different from theirs. Now the integrability use our matrix. Okay. Now, remember the idea is when you have a Lux matrix, you just take the determinant. So determinant for 2 by 2 very easy actually. You just compute the trace of L squared. But you're gonna rearrange your a summation for the trace in such a way. Put all the lambda separately. Put the fractional way in another way. Okay, so basically you can separate two terms. So what is the H sub j we have following? Especially put the box here. This is exactly the Hamiltonian nonlinearization procedure. You get the Lux pair spatial part. Okay, that's I put. That's what we need. So which means this must be here. So otherwise, probably you cannot guarantee the Poisson bracket is 0. So what is E sub j minus, next page, here. This is a little bit longer, but again, the last part is standard. Remember, this is exactly confocal system for finite systems. Okay. Now, this E sub j minus can be, related to another function. I just put sigma of those. You have fk. So fk, you put in a product form. So this is a nice formula. So corresponding to the E sub j minus. Don't forget, our goal is to prove your H is convolute with fk. In other words, your Poisson bracket must be 0. But how to verify? We use our matrix. Okay, so this here, this left-hand side, our matrix, remember, this is on the submanifold. That's why a little bit complicated. Okay, now the right-hand side, you can trace this fundamental Poisson bracket. Because the trace of fundamental Poisson bracket is the commutator minus another commutator. Of course, trace together must be 0. So use our matrix to verify those, Poisson bracket has to be 0. From 21, you produce those must be 0. Automatically results. Furthermore, we can claim this Hamiltonian system, and even those are completely integrable in the sense of a Liouville. Okay, so this is the finite part of proof already done. Just organizer, just let me know what time, if time. Excellent, thank you. So the finite system part is not using our matrix to guarantee the integrability. Now, remember, our PDE people, we're going to do what? What is your solution? What is your purpose to use a finite integrable system? So next part, so use the finite integrable system, related to the PDE. So we're going to construct use of because so those systems are completely integrable. Okay, so those Hamiltonian flows commute. So we're going to build or define the compatible solution, which is compatible. Either you from FQ or H minus, it doesn't matter because they're already commutable. Okay, so defined. So from this initial data, you have the solution Q and K. This is from the ODE. Now, how do we find a PDE solution? Like I mentioned earlier, the key part is constraint. Now, right moment on the M is submanifold. So we're going to rebuild M using your ODE solution P and Q because we already figure out the integrability for the ODE system. So you are 66, give the M is making sense. So M satisfies this hierarchy. Okay, there's negative order. So I put J is this operator. So partial M plus M partial. I'm sorry. Excuse me. So M equals U minus U sub double X. So what is the L? L's in integrability, so called recursion operator. So J inverse K, the computation. Of course, you can compute the inverse of partial M plus M partial. Okay. So this, excuse me, this, so looks like a very small. So this is a solution for the whole hierarchy. Okay. So of course, at the moment, that is a very exact solution, but not explicitly given. So how does compute M in the explicit form? So we give the Riemann theta function. Okay. automatically result is the relative Camassa-Holm equation, because in negative hierarchy, the representative is well-known Camassa-Holm equation. So particularly for PDE or solid people interested in this solution for the Camassa-Holm equation. So those are, so for the Camassa-Holm equation, the finite integrable system H minus 1 and is the convolution part. Okay. So I put this remark: the parametric solution cannot include the peakon solution. We already, this kind of solution cannot include peakon solution. Okay. Peakon solution is separate. Yeah, today's it's a theoretical part. I don't want to talk about peakon solution. Okay, now so from the above part, there's a formal solution. We're going to do what? Algebro-geometric solution for the Camassa-Holm equation. So this part is more pure math part. Okay, first of all, we're going to compute 0 points. Remember, we have Lux matrix. This is Lux matrix. We rewrite, put a lambda 3 there. So this is just a rewrite. LCH equals this. So remember, this is a very standard form for confocal system. Okay, but the first part that you see here, no other, just lambda. Okay, so again, this is under what? Under this simplex submanifold. This of course requires the condition those lambda eigenvalues must not 0. Okay, otherwise you cannot take reciprocal. Okay. The key idea is not from above. You're gonna remember. You figure out the Q1 square and the P. Yeah, because the Hamiltonian has independent dynamical variables, and on the symplectic manner we have 2 conditions. So basically, it's the independent variable only 2 and minus 2. Okay. So we figure out the Q1 square is defined by the remaining Q1 until Q minus 1. Likely Pn is defined as Qj, Pj, but J start from 1 to a minus 1. So independent dynamical variable, just Q1 to Q minus 1, P1 to Pn minus 1. All right. Now we give what? Remember, this is the expression for Camassa-Holm equation. So Q make the inner product with the Q itself. This is the solution of the Camassa-Holm equation. Right now we focus on Camassa-Holm equation in the negative flow. Now we rewrite BH. Remember ABC in the Lux matrix. We have 3 terms. We're going to take BCH now. Rewrite this BCH in the independent variable form. We also put Q lambda, F lambda as a fractional form. So what is a polynomial? So basically those 2 are polynomials. So Q lambda is a minus order or a minus degree polynomial like this. Whereas K lambda in the denominator, remember this here, K in denominator. So in the following, remember, we need just compute figure out what is the inner product of Q itself. Now you find the algebro-geometric solutions. Okay. Now, first of all, for Q lambda, so here we figure out the Q lambda because n minus 1 degree polynomial. It has n minus 1 distinct zeros, mu1, mu n minus 1. We rewrite in such form. Okay. Now, remember, the earlier we figure out the inner product of QQ. This is solution to the standard Camassa-Holm equation. So this part is just eigenparameter, and that part we need to figure out the zeros of summation. So this information gives us you just figure out the summation of those n minus 1 distinct 0 points. You don't have to figure out each one. Okay, just figure out summation. So that's the following procedure we figure out. One of the things our result showed equation number 89, very similar to the result by Aber and other authors. I think that Camassa Holm and Jerry Marston, their paper CNP 2001. Okay, our procedure, remember, we need to figure out dynamic variable P sub j in this way. Okay, now figure out the computation, therefore, you get Pj squared equals this. And our Hamiltonian, I put in blue, okay, this is our Hamiltonian right now. You have to express it in those values, okay? Now in the following, there's a standard procedure to figure out, figure out the generating function related to your solution Q itself inner product, okay? So this is, just a computer rewrite in the rational form. P lambda, K lambda. K lambda we defined earlier. What is P lambda? P lambda is this guy. So this is a standard, the product, but this one is sigma standard. Okay. E alpha is earlier. This part, the E alpha, the earlier we gave you, is actually confocal system. Okay, now we computed the Pj squared and E sub 1 related by that constraint. So finally we get generating functions. Okay, so P lambda and K lambda is well defined already. This is a standard way. I don't want to waste your time. This is just computed, And finally we get H1 H minus y in such form that the x flows already linearized. So linearized, which means under those procedures, we want to integrate it in the explicit form. Under new system, under new coordinate system, that k idea still using the Liouville. Excuse me. Now you see here f h1 and f minus 2. So T flow becomes that. Remember, lacks a spatial part and time T part. Okay. All right, and there's a computation. Finally, you need to figure out the two residues. Okay, because remember, we need to figure out a sigma. So those are summation of the 0 points, the n minus 1 0 points. Not each one. Each one probably don't know, but we need to know the summation. That's it. So these are our major results. I put key number 5. This is residue, sigma, I'm sorry, infinity 1 and residue infinity 2. So here's the computation. You see here, 0 and 0, those two residues, okay. Okay, the residue computed is actually a Riemann theta function. Riemann theta function you add to 3 and k and eta 1 and 2. This is on the algebro-geometric curves. Okay, there's using the procedure. I skip many procedures. So finally, I just show you the solution of the Camassa-Holm equation. So inner product QQ equal first part is a parameter, eigenparameter. Second part, we're using the Riemann theta function. Make the minus, I put the log, okay, because you already take derivative. So some people working on the integrable system, this part probably relate to the tau function, because I'm not sure. So this is a function that depends on your algebra curve. There's a Riemann-Roch constant used in the pure math part as well. So finally, we get the Camassa-Holm equation, the algebro-geometric solution. R is constant. I think the most of my talk today, but I leave some open questions. It's just some people working on the integrable system and related to our matrix. So one of the things, a discrete spectrum. Remember, when people work on the KdV equation, one of the problems is a discrete version of KdV equation. Of course, corresponding, you should have a discrete eigenvalue problem for the KdV equation. So what about the discrete the Camassa-Holm equation? Use symplectic map. Now one on paper by Zhijun Qiao and you can take a look at that. In my talk, so our matrix structure actually is the 2 by 2. What about the 3 by 3 generalization? In the 3 by 3 eigenvalue problem. So the 2 by 2 spectral problem, I did some framework. This is a part of my PhD dissertation. Okay. But for 3 by 3, it's really complicated. But I believe we should have some way to figure out. So like a Bosnian equation or other equation, 3 by 3 eigenvalue problem. The other thing is that the nonlinear evolution equation on the spectrum submanifold, Camassa-Holm is done. What about the other equation, Degas-Paris process equation? But the peakon model is still open. So Degas-Paris DP equation by Hou, Zhao, Fan Gui, Jiao at Fudan University. And the other thing is that how many L's, which means I give the Lax matrix L. This in this Lie algebra, so SL cross product with C. Okay. What about how many? We don't know. Probably I need to learn from algebra mathematicians. Okay. Our matrix satisfying is not uniquely defined. So our matrix actually is that fundamental bracket is not unique. Thank you so much.
Thank you. Are there any questions?
Hey, so my impression is that all this construction is based on this constraint that you impose. But what's the principle behind this constraint? I mean, not like a random constraint. You can make an R matrix out of it, right? So.
Okay, let me back to the slides.
Yeah, right. Mm-hmm.
So first, I address you the question regarding constraint. Second, regarding the matrix.
Mm-hmm.
Yeah, that's a key part in my procedure. Actually, constraint method is here. No, I'm sorry. Earlier. Too fast? Get frozen?
Yeah, I think it's.
Our matrix.
Yeah.
I'm sorry.
Next.
Here. By Professor Cao. Yes. Here's the key idea for the constraint method. Mm-hmm. Okay. The starting point is eigenvalue problem. Uh-huh. Suppose you have eigenvalue problem here. This is eigenvalue. I write it in matrix form. So, but sometimes in scalar from either second order or third order. Mm-hmm. If second order, so here it would be 2-dimensional vector. So M is 2 by 2 matrix. Mm-hmm. And U is the potential function. Okay, lambda is an eigenvalue. So this is constraint. Mm-hmm. So constraint is, the U is a potential vector. The Y is eigenfunction. Question, how do you find the F?
Right, exactly.
Okay, this is related to integrable hierarchy. What I showed you for the Camassa-Holm equation, let me show you. You are asking the right question, how to find the constraint. In my presentation, I'm sorry, I should go forward. Remember that I put G minus 1. Mm-hmm. Actually, that part is from Lanata sequence. The key part is use 2 operators, produce the hierarchy. Mm-hmm. The hierarchy, you have the generator. Mm-hmm. The G part, G minus 1, actually is right here, something like this one. This is from the left-hand side, actually is from the kernel element of the 2 operators. One of operator is a K, the other is a J. This is a recursion, we call Lanata operators. Mm-hmm. Let me show you what. Looks like it get frozen again. Okay, so remember that you have the left-hand side 1, right-hand sigma. Left-hand side is kernel element from one of the nada operators. Right-hand side, you compute actually square eigenfunction. We call the functional gradient of the eigenvalue with respect to potential function. Yeah, that's the relationship.
Okay.
Okay. That's the first point. The second point regarding matrix, our matrix structure. After that, you need to figure out, remember, nonlinearization exactly here. So this is a so constraint. You plug in the constraint. Based on that, you need to figure out the integrability of this finite system. So our procedure to figure out our matrix. Use our matrix to find those system of functions, which are in evolution. In other words, the Poisson bracket must be 0. Then use the system of functions, you verify the Poisson bracket of those functions with your original Hamiltonian. Then we claim that system is a finite integrable. That's the procedure.
Thank you. Is there any question? Okay.
Here, question. Professor Zhang. Later.
Okay.
It's up to you. Yeah.
Okay. Then let's thank the speaker again.
Thank you.